also another problem that many people have is once you train a model, they want to interpret the model to understand what the model has learned, right? There's a trade-off between the accuracy and the interpretability of the model, right? If you look at these two axes, right? The models like the linear regression, logistic regression, and models, things like that, right? Which has a low accuracy but high interpretation. On the other hand, you have the models like neural networks and deep learning and things like that, right? Which has a very high accuracy but very low interpretation, right? So random forest is kind of in between here, right? You can try to interpret a random forest model, at the same time you can get sort of like a high accuracy, right? And this is very important. The difference between data science and software projects. I guess most of you are from software industry, right? So this is the main difference. So in a software project, basically you start with the business requirement, right? And then you have a final deliverable, right? Which is a software system basically, right? And for data science, you again start with like business requirements, right? And you have final deliverable, which can be a software, slide deck, or a report. But this is the thing, right? Important thing. So that you have to play with the data. Data contains a lot of uncertainty, right? Until you analyze the data, you wouldn't know whether it contains any value, right? What are the problems contains there? Because of that reason, right? You would expect to achieve, right? You expect to basically to get the rabbit out of the hat by applying the magic of machine learning to data, but you have to prepare for this, right? So when you apply data science for data science projects, right? Okay, so this is that. Let's say you have get everything right in the pipeline, right? Still, you can get this situation. That is that you wouldn't get any uplift at all from your model. Your model may not work at all, right, compared to the control group. This may be the reason it's called the signal versus noise. That is that even though you use the best model that you can train on your data set, right, the noise of that particular thing that you are trying to optimize is too much than the signal. Because of that, you won't be able to get any uplift from your model at all, right? So those are the technical details. Finally, the communication issues. Basically, you have to always deal with the business people. You have to get the requirements from the business people, and you have to communicate the results back. And then you have to communicate with the engineers, right, the data scientists and the engineers. There are a lot of communication problems, right? So the best thing is to keep open mind and listen to each other, right? Because these people would talk different languages, basically, right? So you have to keep open mind and listen to them. So finally, if you like to become a data scientist, I'm giving some tips. Basically, there are two sides of this data science and big data analytics. One is the data engineering, right, which involves all this database management and data plumbing and software engineering skills, which are called data engineers nowadays. And the data science side of things, right, which involves the data analysis, feature engineering, modeling, all this analytics side of things, right? So if you want to be a data scientist, basically, so these are the skills that you should develop. Statistical skills, machine learning is very important, right? And some mathematical skills, that is optimization, like linear algebra, that kind of stuff. And in terms of programming, you can start with R or Python, right? You can develop these skills later on, but R or Python, or right, you must learn something like any of these things, right? And also the good written and verbal communication skills, and creativity is very important, because as you have seen, right, there's a lot of points of failure, right? So you have to be very creative, identify the problems, and turn things around in this pipeline, right? And these are some of the good resources that you can follow, right? Some of the data science courses at Coursera, right? And also the machine learning courses at Stanford, at Oxford, and CMU I would recommend, right? Which are on YouTube and in Coursera. And these are for large-scale machine learning. The New York University had a very, very interesting large-scale machine learning course in 2013. You will learn about Vowel Rabbit and other deep learning stuff like that, right? And also some of the web pages, and also top conferences about data science and machine learning. So I'll conclude my talk with two slides. That is that big or small data is very important, right? So you have to collect and analyze data. Otherwise, you will be a person with just an opinion, right? So the data collection and analysis is very important, but you have to get it right, right? So everyone claims that these days they are doing big data and data science, right? And nobody really knows how to do it. Everyone thinks that everyone else is doing that. So everyone claims that they are doing it, right? Just for the sake of doing that, right? And with that, I'll conclude, I think, my first talk. Yeah, thank you very much.
We'll start the next presentation now itself. Sorry for the people who are standing. I mean, we didn't expect this much of crowd. We'll start the second session right away, and then we'll move to the panel discussion.
about deep learning. So deep learning has been the technique people use to solve AI problems for the last several years, right? So I basically want to give a brief introduction to all the state-of-the-art techniques being used at deep learning, and the reasoning behind that of using those techniques, some motivation and intuition behind those techniques, and some applications, right? So the area of AI was started around 1950s with the aim of developing intelligent machines. You may have heard enough of these definitions, right? So during your last talks and things like that, right? What AI means and things like that. Basically, there are two research directions of AI. One set of groups trying to solve something called artificial general intelligence, and the other one is artificial narrow intelligence. In artificial general intelligence, we are trying to solve the main characteristic of intelligence as a whole, right? Like learning and reasoning, planning, adaptability, vision, speech, autonomy, and so on and so forth, right? And trying to develop machines having all of these, most of these characteristics together, right? In narrow AI, basically people concentrated on each of these characteristics separately, right? And try to solve them separately, basically, right? Which gave rise to lots of applications in these different areas like computer vision, speech recognition, and navigation, and so forth. Let's look at what an AI problem is, right? So because of that, we'll define what a computer program is. Computer program, you can define it as some sort of a mapping from set of inputs to output. If you know how to do that mapping as a set of mathematical functions or a set of rules, you can implement that, right? But there are a lot of problems in the real world you don't know how to solve. For example, if someone asks you to write a program to separate cats from dogs, right? You know that your brain does it for you, but you don't know the recipe or the algorithm to write it down as a program, right? So these kind of problems are you can name them as AI problems, right? So the way we solve this problem is basically using machine learning methods, right? In machine learning methods, as we discussed previously, we collect a lot of examples, right, of these different things that we want to learn, right? Then we train a model, right, to do the particular task, in this case to separate cats from dogs, right? So people have been trying different machine learning techniques over the last many decades, right, which we can categorize into different main categories. So people start with using something called logic-based methods, right? Some deductive logic, inductive logic programming, fuzzy logic, having some uncertainty to the logic and things like that. That are logic-based methods, right? Then you have the connectionist methods. So the neural network comes under that. I also have the evolutionary methods, which includes genetic algorithms, right? The genetic programming, which follows the sort of like the natural evolution, right? Characteristics to come up with best programs, things like that. And we talk about some statistical methods, right? Like frequentist method, like regression models, and Bayesian methods, sort of like something called the Bayesian networks and things like that, right? Involved with using statistics to handle the uncertainty of that learning part, right? And also we have something called similarity-based methods, right? So there are techniques called support vector machines and kernel methods and things like nearest neighbor methods come into that category. And also people use hybrid methods, combinations of many of these methods. So in this talk, we mainly focus on these connectionist methods, and we are going to talk a little bit about neural networks. So I'll start with giving a brief introduction to what artificial neural networks are, right? So we'll start with sort of like a biological neuron. So we know that we learn brain, the brain contains biological neurons, right? You can think a neuron as a sort of like a processing unit, which accepts some inputs, which does some processing, and which produces some outputs, right? And how does the learning happens in brain? Basically, you have the connection between these different neurons, and there are chemicals between these locations, which is called the synapse, the location, and there are chemicals, right? When you try to learn something, there's some modification to this chemicals happen, so because of that, the learning happens. That's the sort of like the well-known theory of human learning, right? So far, right? So the human brain contains about 10 to the 14 of these connections. Because of those large number of connections, you would be able to learn a lot of things throughout your lifetime, right? So, so this is a biological neuron we saw previously, right? So people have been trying to sort of like come up with a sort of artificial neuron which will mimic the biological neuron, right? Which you can use to learn things in a machine, right? That is that you have inputs, right? You have output. You can use these something called the weights, right, in your model, which mimics the chemicals, right? Then what happens is you basically do some operation calculation here. Basically here what you can do is you can get this weighted sum of this input with respect to these weights, and you can use a function to modify the magnitude of the output. Basically you can squish it between like 0, 1 and +1 and something like that, and you can produce the output. At the learning time, what you can do is you can use some algorithms to modify these weights, right, in such a way to get the best mapping between inputs and outputs, right. A gradient descent algorithm I just mentioned previously is one such algorithm, right. So this this artificial neuron was introduced in 1960s, which was called a perceptron. So usually people use this gradient descent algorithm to train these weights, right. That's a brief introduction. So this is the same picture there, right, that we saw previously, and like this, the function that used here, right, people have used different functions, right. This is step function, that is that if the sort of like the magnitude of this part is greater than some value, you fire some signal, otherwise not, something like that, right. Here you can use a linear function, which is equivalent to something called the linear regression model, if you use that in statistics. If you use something like a logistic function, so a function like that, to squash your output between 0 and 1, so it would be equivalent to logistic regression in statistics, right. So this is single neuron, right. Then what you can do is, right, you can connect more than one neuron in a sort of like a layered manner, right. So which is called an artificial neural network, which has a very higher capacity of learning things, right. So this architecture, once you have these neurons which are connected in layers, right, you can have multiple layers, you can have these connections or the weights between layers, which you modify during the learning, right, and this kind of a model is called a multi-layer perceptron, because it's a combination of this simple model called perceptrons, right, and which is also something called a nonlinear model, right. So people use something called the backpropagation algorithm to learn these kind of neural networks. That is to find the best optimal set of weights to map these inputs and outputs, right. I'll skip that, right. So next we look at how these artificial neural networks have been evolved over the last couple of decades, from simple artificial neural networks to deep learning systems that we talk today. So before 2006, right. So artificial neural networks were quite popular around 1960s and 80s and 90s, right. Worked with some sort of like small scale pattern recognition problems, things like recognizing handwritten digits. There was a system used by US Postal Department to recognize handwritten digits in envelopes, right, developed by the Professor Jan LeCun, right. So it was called LeNet, right, was used in 1998. But with the development of some other algorithms like support vector machines and so on, right, around like early 2000, the popularity of artificial neural networks went down, basically. This is due to main couple of reasons. That is that there were some technical problems, things like there was something called local minima. That is that once you train the network, sometimes you try to find the solution which is not the optimal solution that you can find, right, which is called the local solution, right. And also people were unable to train models with more than 3 or 4 layers of neurons due to the problems like overfitting. That is that in the training data set, you would get a better accuracy of the model, but once you test the data set, once you test the model on the testing data set, you get a very poor performance, right. And also there were technical challenges, something called the vanishing gradient problem. I'm not going to describe what that is, right, but if you're interested, you can look it up, right. Because of these reasons, right, people were unable to train the neural networks with more than 3 or 4 layers. Due to the same reason, people were unable to solve complex problems using neural networks at those days, right. But there were a couple of people who continue with their research on neural nets, right. Things like Jan LeCun, right, especially these 3 people, Jeff Hinton at University of Toronto and Yoshua Bengio at University of Montreal, right. Then what happened after 2006 is very interesting, right. Several major breakthroughs happened, giving birth to an area called deep learning, right. So in deep learning what we have is nothing but the good old neural networks with many number of layers, right. Simply that is there. So since around 2010, right, so the deep learning methods have been significantly outperforming the existing methods in major computer vision and speech recognition, right, problems. For example, ImageNet is one of the famous computer vision challenge, right. So as of today, there are about 14 million images and 21,000 about categories, right. The challenge is to identify, process those images and identify the categories of those images, like so this is called the object classification, identification of those objects within an image, right, and tag them, and also the identification of the location of things in an image and things like that, right. Now, if you look at this object classification challenge, see how the error rate has gone down over the years, right. In 2010, it was like 30% error rate. This is the best performance that they obtained. And when they started applying deep learning in 2012, it went down to like 16%, right? And now it's around 3%, right? And the same with the speech recognition, right? This is one of the, again, quite famous one of the speech recognition challenges, right? So you can see how the traditional methods performed, right? So when started applying deep learning, right, they started, error rate started getting down rapidly, right? So next we look at, so what are those advancements, right, which made the deep learning possible, right? How would people start learning all these very, very deep neural nets, right? So mainly, in order to solve complex problems, things like, if you want to train, if you want to develop a system to recognize general images, right? For example, speech recognition, things like that, you need complex systems, right? Neural networks with a lot of layers, because we have to represent a lot of knowledge into those systems, right? In order to train very complex systems, you basically need 3 components. First one, you need a lot of data, right, to train a lot of large systems, complex systems. I mean, with the era of big data, this is not a problem today, right? We have lots of data in the internet, right? You can find, or elsewhere people generate and save data. That's what we talked about yesterday. Because of that, finding a lot of data is not a problem nowadays, right? The second thing is the advancement of the computer technologies, right? You need to train complex systems, you need complex or the advanced processing and storage or the memory and that kind of facilities. So people had started using GPUs in addition to CPUs to train models, and also you don't have to own any of these machines nowadays, because you can use cloud computing, right, to get GPU cluster or something to train your deep neural network model, right? So the next one is the advancement of algorithms, right? So people came up with new architectures of neural nets, and also they use different tricks to improve the training algorithms to get rid of all those technical problems they had in a couple of years back or 10 years back, right? So next we are going to talk about mainly these algorithmic advancements of deep learning, right? So the main concept of deep learning is this, right? That is that in traditional machine learning, right, if you want to train a model, right, so you have the raw data, right, then what you have to do is you have to do something called the feature engineering, come up with the characteristics described in the data set, right, and you have to do some feature pre-processing, making the features ready for the modeling, and then you can train the model with those features, right. So this, okay, so the task would take about, as I mentioned previously, 80 to 90% of your effort, like human effort, right, to come up with these features and do the pre-processing, right. In deep learning, the advantage is you can start with raw data, right. When you apply a deep learning algorithm, it would learn both the relevant features and the model for you. You wouldn't need to do any of this feature engineering. That's a big advantage of deep learning, right. So the feature learning is, another name for feature learning is called the representation learning or embedding learning, right. So this is an example. Let's say someone has trained, so this is a real world example because someone has trained to recognize images using this very large neural net, right. So once you look at what each of these layers have learned, you'll find that, right, in the first layer, so you start with pixels. Pixels are the raw inputs to this image, and you have labels calling this is the name of the person or something like that, right. Once you have done that, you identify that the first layer has managed to learn to identify the edges, the very primitive features, which are the combinations of those pixels, right. And the next layer started identifying some combinations of these edges, like something like the part of the faces and things like that, right. For example, when this neuron sees this part of the face, it will send a signal. Otherwise, it would not send a signal out, things like that. So the later layers started identifying more complex patterns, things like that. So people have started identifying that once you train a neural network like that using these deep learning methods, right. So these layers started learning these hierarchical, compositional, right, layer features of different complexity automatically, right? Which is a very, very good advantage. So next we look at, so what are the techniques people apply to learn these features automatically, right? There's one technique called layer-wise unsupervised learning. That is that in order to do that, people use neural network architecture called autoencoders, and especially something called the stacked autoencoders, right? Next, we look at what an autoencoder is, right? In an autoencoder, this is a particular neural network basically, right? We have 3 layers. What you can do is you use the same data set as the input and the output, right? The same input you use as the output, right? What you do is you try to encode that knowledge into some compressed representation there, right? Here, so you have an encode from V to Y to V and a decode from V to W, right? So if you do that, people have identified that this layer, the hidden layer, managed to learn the edges from the input pixels, right? That's that. So then what you can do is, right, you can learn these layer one at a time separately, right? Here in the first time you learn the edges, right? In the second time what you do is you use these edges, right, the middle layer that you have learned as the input layer, right? Try to learn some combination of these edges separately, right? The third time you use this layer, right, and try to encode that into some higher level of features, right? So you do it sort of an unsupervised manner. That is that you don't use any label to do that, right? Then what you do is once you have learned all of these features separately, you can stack them up. You can connect these layers together and then train this neural network using the label, using a supervised learning, right? So this technique called feature unsupervised or layer-wise unsupervised learning. That is that first you do this layer-wise unsupervised learning to train learn features automatically. Then you use those features to learn something in a supervised manner, right? So this is another architecture people do the same thing, which is called the deep belief networks. There also you learn layer by layer, right, unsupervised manner, right? So that's sort of one approach. The second approach is, right, people try without doing that unsupervised feature learning. People have found ways to learn both features and the model using supervised learning, right? So they don't do any pre-supervised, unsupervised pre-feature learning. They used only supervised learning, the second part. But when you do the supervised learning, you can learn both parts, the features, the relevant features for your model, and also the model, right? For that, people use 2 architectures mainly. These are the most popular architectures. One's called the convolution networks. The second one is called the recurrent networks, right? Let's look at what those are very briefly, right? So let's look at what a convolution operation is. Let's say you have a feature image like that, right? Convolution is a sort of like feature extraction method from images, right? So let's say you have a matrix like that, which is called a convolution filter, right? So what you can do is once you apply this convolution filter, for this image, you'll get an image like that, which would highlight the edges, the thing that you are looking for. Here within this matrix, you are trying to highlight the edges. You are trying to identify those features in that image. That's what you're trying to do, right? How would you do that? You get that pixel patch and you have this corresponding filter. You simply get this dot product between those 2 values, right? Once you have what you are looking for here, you get a higher value for this Z, right? So in traditional machine learning, what you have is you had to define these filters to get the features out manually, right? With respect to different tasks that you are trying to solve, right? So basically, you had this original image, then the people had to come up with these different filters manually. People applied the filters, did some feature engineering, right? You had the features, then they train the model in classical machine learning. But when you apply a convolution networks, what you do is you can get these model plus these filters learned automatically, right? You don't have to do any feature engineering. How would you do that, right? So you have input image, and you have these different, so you can think of these as different layers of the neural network. Each of these layers is represented by a set of neurons, right? So what you do is basically you can combine, you can connect all the neurons between these layers, right, in a sort of like a sparse manner to represent those corresponding filters, right? How it is done is a bit complicated, right? It would take some time to explain, right? I'm not going to do it here, right? If you're interested, you can look into that. But the thing is, main point is you implement each of these layer as a set of neurons, and you connect those neurons between layers in a different ways, right, to represent those different filters. But what you learn at the training time is you learn the model, or at the same time you learn the values for those filters as weights of the neural network. So that's the main idea, right? So that's that architecture called convolution nets. The second most popular architecture is called the recurrent nets. In convolution nets, what you have is you assume each of the input is IID, right? It's statistically identically distributed, right? That is that the second input doesn't have any relationship with the first whatever that you use to image, things like that. But in real world, there are some other situations like a time series, right? Think about time series like that. In a time series, right? So you know that there are some relationships between the next value that you see in the time series. It may be the relationship with respect to a recent value or a value that you have seen in, right, long time ago, something like that, right? So for example, if I give you an example, if I ask you to tell me the alphabet from Z to A, right, or A to Z, which one you prefer? A to Z, right? Another question, if I ask you to tell me the fourth character from your name, can you recall like that? You can't, right? You have to start from the beginning. So because that is that some information we store in the brain is sort of like this sequential information. There's no random access for in that case, right? You know, okay, so you get the point, right? So in order to learn such things, right, like this kind of things, this kind of patterns, right, you need to have learn some relationship between all these inputs, sequence of inputs that you see, right? In order to learn such things, we use these recurrent networks, things like that. For example, the same patterns that you can find in voice segments, right? For example, if you want to predict the next word that should come out from my mouth, right, which has some relationship within all the words that I have used so far, something like that, right? And the same thing with language modeling, and same with the writing patterns as well, right? So so this is the sort of the architecture of a recurrent neural network. That is that. So basically, the input to the current. So what we do is basically, so we use the loops, right? We use the loops to implement these dependencies between the inputs of the what you have seen so far, right? Basically, the input to the recurrent network is the current input part plus some combinations of all the inputs that you have seen so far. That's the trick, right? Because of that, this recurrent neural network maintains some sort of a memory of what we have seen so far, or what you have output so far, things like that, right? But there's a problem with this standard or the vanilla version of recurrent neural networks. That is that it was very difficult to learn very long distance relationships, right, with this recurrent neural networks. Because of that, people introduced a different version of this recurrent networks called LSTMs, which is called long short-term memory networks, right, which has the capability, rather than just remembering what we have seen so far, which has the capability to modify it. That is that you can decide to delete it, you can decide to modify it, you can delete it whether to output or not, right? You can do all these different decisions based on, you can modify your memory basically as you go, right? How would you modify that? You learn those actions automatically again, right, when you train the network, right? Because of that, you can automatically learn all these short-term and long-term dependencies if you use a LSTM kind of a neural network, right? So that's the only sort of like the theory part that I'm going to cover, right? So next we look at some applications, right? Basically, so people have been using these convolution nets and the recurrent nets and LSTMs to perform different tasks like face detection, recognition of handwritten digits, right? Tagging different objects of the images, and generation captions, right, of the images, and coloring black and white images, and reproducing images and things like that, right? Okay, and also for the speech recognition, right, handwritten character generation, and the generation of text. For example, in this example, they have trained a recurrent network with the Shakespeare's text, and after training, right, so the network managed to produce text which would look like Shakespeare's writings, right? It has managed to capture that pattern somehow, right? and for language translation, and also for speech generation. Once you have a text, we can generate the speech using these kind of different techniques, right? Next, we briefly look at what are the sort of motivations behind this feature learning, automatic feature learning, or this feature represent, which is called also called the representation learning, right? So one thing is, obviously, right, it would cut down the effort of handcrafting features. You can learn features automatically. You no longer need to, right, so do feature engineering, right? And also, as humans, how do we learn things is very important, right? Usually the way we represent knowledge, our knowledge in our brain is sort of like a hierarchical, distributed, and compositional manner. Think about the language, right? So basically, the language contains we have characters, then we have the combination of character words and the sentences, right? The documents, books, and disciplines and things like that, right? So this is a hierarchical compositional representation of knowledge, learning things, right? The same with problem solving, right? When you, as engineers, when you try to solve problems, you break it into smaller parts, then combine those parts to solve complex problems and things like that, right? Language, and it turned out that how we recognize patterns in the brain is sort of similar, right? So we recognize pixels, right? Then some neurons would recognize the collection of pixels, some edges, and some combinations of edges, the complex patterns, and so on and so forth. Different layers of neurons, right, have been fired when we try to recognize images, right? So these have been found experimentally. So this is the same thing we are learning with deep nets as well, right? In deep nets, we learn these layer-wise, like complex features, right? Compositional and hierarchical features,